In this section, we're going to be engaging more heavily with the derivative, looking at some of its applications and interpretations. And that's what we want to talk about first, how we interpret derivatives and the results we obtain from those. So derivatives tell us about the rate of change of a function. This is very similar to the idea of slope for a straight line equation, but we generalize that to say rate of change because functions that curve can be increasing and decreasing at different points. So it's no longer a constant slope, but a rate of change that can be different at different points along our function. If we evaluate f prime of x, where f prime is one of our notations for the derivative of a function, if we evaluate that derivative function and we get a result that's positive, then that means the function is increasing. Just like with slope, a positive slope means we have an increasing line, decreasing slope means a decreasing line. If we evaluate f prime of x and get something that's less than 0, that means our function is decreasing. Negative rate of change, decreasing function. That's one thing a derivative result can tell us. It also lets us approximate our function value if x is increased by 1 unit. And we'll take a look at that idea in example 1. The total cost in dollars of producing x items of a particular product is given by this cost function c of x. We want to use Symbolab to find the marginal cost function. The marginal cost function is just the derivative of the cost function. There are two different ways that we can designate, well, there's more than two different, there's a couple of different ways that we can designate that what we want is the derivative of a function. So let's introduce some notation quickly over here. So what we've already used is that prime notation. So we could say, for instance, c prime of x, f prime of x. We could also use the notation d over d of x of our function c of x. So that's telling us to take the derivative with respect to the variable x. Or that can kind of get condensed a little bit, and we could write something like dc over dx. We'll primarily look at those first two notations, but all three can be used. So in this case, if what we want to find is the marginal cost function, then we want to find c prime of x. That's just the specific name for the derivative of our cost function. To do that, in Symbolab, we'll use that d over dx notation to tell it, to communicate to it what we want is the derivative of this function. And then we'll input that cost function that we were given. After we evaluate, it'll give us that output, telling us that our marginal cost function in this case is negative 0.8004x plus 36.5813. Now what we want to do is use Symbolab to find the following results. We want to come up with c of 13 minus c of 12. Since there's no little tick mark there, that's not evaluating the derivative. That's evaluating the original function at 13 and 12. So we would plug those into c of x, that original function, and we would generate 2,556.0384 minus 2,529.4621. And then subtracting those two results would give us 26.5763. Then that next piece is asking us to evaluate c prime of 12, which in this case would be using that derivative function we just calculated. So we would plug in x equals 12, and we would get a result of 26.9765. In part C, we want to interpret that information. The exact cost of producing item number 13 will be $26.58. This is the value that we got, rounded, from taking C of 13 minus C of 12. Because whenever we evaluate the cost function, that gives us the total cost of producing that many units. So if we subtract the cost of the first 12 units out of C of 13, we're left with just the cost of producing that 13th unit. But what C prime, that marginal cost function, tells us is that the approximate cost of producing item number 13 would be $26.98. So what we have is an approximation for calculating the cost of that 13th item that we generate using that marginal cost function. It tells us at a production level of 12, if we increase production by one more unit, what that additional cost would be. Let's look at one more example here, where we have the total sales of a company in thousands of dollars t months from now, given by this function. We first want to find use Symbolab to find that marginal function, to find that derivative function. In this case, I'm going to use d over dt, because the variable in this problem is a t. We'll select that square root from the palette up above, so we'll take 9 times the square root of t plus 19 to get our derivative function. So s prime of t will be equal to 9 over 2 times the square root of t plus 19. And then we want to use Symbolab or a calculator to find s of 17 and s prime of 17. Doing that, going back to the original function and plugging in t equals 17 would give us 54. And evaluating that derivative function, s prime at 17, would give us 0.75. What that's telling us is that after 18 months, because whenever we look at the derivative function, it tells us the value if our independent variable is increased by 1. So in this case, if t was increased by 1, so from 17 to 18 months, sales will total approximately the sales we had after 17 months plus the sales we had, how much our sales would increase in that next month, to be 54.75. But then the very last thing that we need to take into account here is that this is total sales in thousands of dollars. So we need to take that result times 1,000 to get that our approximate for our total sales after 18 months would be 54,000. $750. And again, this is the idea of what marginal analysis is going to get into. We're getting an approximate for what our function value would be if our independent variable, in this case it's t, in example 1 it was x, was increased by 1 unit.